Welcome to Breadboarding. This is video 41 in the Breadboard 8088 PC series, and in this video I'm going to continue to convert the floppy disk controller from DMA to programmed I/O. And with these changes, hopefully we're going to now be able to boot later versions of MS-DOS such as MS-DOS 3.3, 4.01, 5 and even 6.2.2, which were unable to boot to due to problems with the DMA controller. So this is our overall high-level plan. So the only bits really of our basic floppy disk PC down here, when we were trying to run different versions of MS-DOS, I was trying to run, in addition to PC-DOS 2.10, MS-DOS 3.3, MS-DOS 5, and I was unable to get those working with the DMA controller. So in the previous video, which there will be links at the top of the screen and also in the description below, in the first half I covered doing programmed I/O. So this basically means using the CPU to poll the floppy disk rather than using the DMA controller, direct memory access controller. So these are all the steps involved in the DMA hardware reading data from the floppy disk, and I covered this in the previous video, so I'm not going to go into it in detail. But the main thing here is that a lot of the time the CPU just waits for an interrupt. So although DMA theoretically frees up the CPU to do other stuff, in fact on the original IBM PC, certainly under DOS, then basically just was spinning in a loop waiting for the interrupt to occur when the floppy disk drive says I've finished. So this is the simpler mechanism which the programmed I/O uses, and basically there's a loops where the floppy disk drive is reading the data and our CPU checks a status register and then goes through and processes the data, writes it to RAM, and then goes round until such time as everything is finished. Now what we're going to come to in a minute is there are some issues to do with the way how the floppy disk controller is told to end. Under normal circumstances, the DMA controller sends a signal to the floppy disk controller to say I've finished, I've got all the data I need. So the terminal count or end of process coming out of the DMA controller. So this was the diagram I was explaining what was going on. Again, this is all covered in detail in the previous video. Basically all the stuff in orange here is really the surplus stuff that we don't need if we can get rid of the DMA and actually use programmed I/O. Now I mentioned in the previous video that the PC Junior, which is an IBM sort of consumer PC, didn't use DMA and use programmed I/O, so I've used quite a few of the resources here, which again, if you want to look at these in detail, skip back to the previous video, which I'll include the links in the description below, and that includes how to do this. And then we talked about the diagrams for how the PCXT floppy disk controller differed from the PC Junior. So there's some things to do with watchdog timer, which we might want to introduce at some point in time, but certainly we don't need to for the purposes of this exercise. So one of the things I did mention is that the floppy disk controller data sheet was incorrect. Some of the labeling of the various tables and things was not right. But I also want to just highlight there's a couple of key things really in here. So in the main status register, we're really worried about a couple of bits. So there are the standard ones which are used for communicating with the floppy disk controller. So request for master and data input, basically when the floppy disk controller signals that it's ready to either input or output data. But there's two other ones which are important. So execution mode is only used when we're in non-DMA mode, so when we're in the programmed I/O mode, and also FDC busy. Now FDC busy I made some assumptions about which weren't quite right, and I'll explain where I got that from in a minute. So the key thing really is FDC busy is cleared at the end of the results phase. So this will remain set for the duration of the sending the command, executing the command, and then reading the results. So only once all the results have been read will the FDC busy get cleared. And execution mode starts off at 0 with the command. Once the command's been sent, it will be set to 1. During that period of time, we would be polling the floppy disk controller for reading and writing data to it. And once execution mode goes to 0, then we're in the results mode. So these are some of the key things we need to be looking at, which you don't have to worry about with DMA. So the status information that comes off status register 0 down here, there are two bits here at the top, D7 and D6, that tell us whether we got normal termination or whether there's some sort of abnormal situation. And there's also a bit here, seek end. So a number of commands that return seek high, seek end high when the seeking has completed. There's another one here, end of cylinder, and we'll come to this in a minute when we talk about how we tell the floppy disk controller that we've got enough data. We don't have to worry about these other status register. So I just highlighted here that there are a few things on this thing. So we needed to be aware that of these bit D7 and D6, and also the seek end, but also that under error situations then the bit 7 will also be set when there's an incorrect command. This other bit that we need to worry about, the no DMA, so we need to make sure we set that correctly in all the code. I won't cover all the IRQ6 stuff here, but handling the error when sectors returned does not match the sectors requested. This is all to do with how do you determine when the floppy disk controller has actually returned enough data and we can tell it to stop. Now there was some additional information. So this status code about invalid command came from the original IBM PC floppy disk controller documentation, and there was some extra stuff in the data sheet that I came across. After each byte of data is read or written to the data register, the CPU waits for 12 microseconds before reading the main status register. This was one of the first steps when I was looking at getting this to work, whether we need to allow for 12 microseconds between reading or writing to the data register and then next checking the status register. And then the other bit of data here, really, command busy, set when the command byte is received, cleared at the end results phase. So you'll see that when we're collecting the results from the floppy disk controller, it's only when the last result byte is returned that this will get cleared. Now I had some new problems to address. So the PC Junior used 5¼ inch 360k floppy disk drives, I think. Now they work at a lower data rate than the high density ones that we're using, so we'll be using the 1.4 megabyte floppy disk drives. There was an issue that I hadn't anticipated in that working at half the data rate, then the code has about 31 microseconds per byte to poll the floppy disk controller and to read the byte and write it to RAM. However, we have about half that amount of time when we're using the higher density drives. Now the problem is the default PC Junior BIOS code was not fast enough at our 4.77 megahertz frequency for 1.4 megabyte drives. So a number of things which I'll show you that I did to solve this. So I had to improve the efficiency of the code. So there were multiple tests and multiple jumps and they were just taking too long. So I managed to refactor the code so that we have a single test. And by making use of this jump not sign, which basically allows us to test the D7 bit, which happens to be used by the ready status. And this allowed me to do one test and used two conditional jumps after it, which saved a couple of clock cycles. There's also techniques such as using registers for the status values if we are checking status values rather than an immediate byte following on from the instruction, and this saves about 2 clock cycles, I think, where it's used. And then finally, jumps can also jump to a register value, not an immediate value or relative value, and again that saves to a couple of clock cycles. So with these changes here I was able to make quite an improvement. Then I had to disable the IO wait states. That meant that the IO read and IO write went from 600 nanoseconds down to 400 nanoseconds. This didn't seem to really cause any stability issues. And then finally I increased the base clock from the 14.3 megahertz which the original PC used, which is then divided by 3 to get to the 477 there, and I increased up to 16 megahertz. So this is slightly above what the process is supposed to do, but it's probably within tolerance. So it seemed to actually give me a few more microseconds. When we were running at the 14.3 megahertz, managed to get it so that when it was reading 512 bytes, it was missing about 5 of them. And with this extra boost in frequency, then we're able to get all 512 bytes and didn't have any missing data. Now, I think with some of the further optimizations I did, I might possibly be able to switch the crystal back to 14.3 megahertz, but I've been trying to get this working for quite a long time. So for the moment, I'm just keeping it in its working state. So let's take a look at some logic analyzer outputs and things just to show some of the stages that I've had to go through to fix this. This first one's actually coming from an earlier trace I did with the MS-DOS 4 debug version, and this is using DMA, and this is showing the floppy disk controller read to read times. So you can see here that we've got the IO read from the floppy disk controller. The first byte of the boot sector is EB, and the second byte is 2C or 3C depending on the version. With DOS 4 it was a slightly larger jump here, but you can see here that we've got 15.6 microseconds. So really, unless we can actually read the data within 15.6 microseconds, we're probably not going to be able to keep up. And you can see the way how the floppy disk controller requested the DMA controller to handle the data is by the DAC2 signal here. So the time between two DAC2s, or the two IO reads of the data, will be the time that we need to beat. So to start with, if we have a look at some of the basic signals that we're looking for here, if I go into Zoom here, it should be a little bit easier. So the first byte in the boot sector is EB, and this is the address here that we're reading it from. And we can see here that then after this, we then check the floppy disk controller status. So we read the status from the port 1 lower than that, and F0 basically means all the status bits are set. Now you can see here that the floppy disk controller status to read this period here was about 8.4 microseconds in the default situation. But one of the problems we ran into is that if the timing between the last read and the status values, you can actually get a not ready. So what we have here is we've actually read the data here, then we've read the status, but the floppy disk controller is not quite ready, and then we've actually read this again. And in fact, if we look at the time here, so from the time that we've actually read the last bit of data, check the status first time where it's not ready, then it is ready, then by the time we actually get to read the data, it's actually going to be quite a lot further on than 19 microseconds. So it was running too slow, and so basically we could actually miss data. And in fact, one of the issues I ran into, we ended up skipping bytes due to the timing issues. So you can see here we've got our EB, which is the first byte in the boot sector, followed by 2C. Now when we're handling the first byte here, what actually happens is that the IO signal down the bottom here, when it actually goes high, the floppy disk controller has already started reading the next byte. And in fact, when we save the byte to 7C00, which is the first byte, we actually get 2C and not EB. So this is indicative of some of the timing issues. And so the changes I identified basically have been going to address this. So you can now see that this period of time here is the read time to the read time. So this is now about 16.5 microseconds. So this is much closer to the DMA value, which I think is about 15.5, 15.6. And you can see here again, we've got a situation where, due to timing issues here, that we're expected D0 to be saved, but in fact, because it's moved on to the next value, 02, we actually get 02 saved in the RAM and not the D0 that we expect. And obviously this is not good for booting operating systems. And this is just a little bit more detailed view of it where you can see the two values. The first thing I did was disable the IO wait on the clock controller, the 8284 clock controller. So the /AEN input was basically just unplugged, it was tied to ground. And what this will do is to change the IO read and IO write period from 600 nanoseconds down to 400 nanoseconds. So this is the value here. We're still getting the problem, so we're expecting 018, and in fact we get 07C. So even with the unplugged IO wait here, we've got IO write, IO read is now 400 nanoseconds down from 600, but it's still not quite enough. So I was looking then at increasing the clock speed, and at this point in time when I was doing this, out of 512 bytes per sector, I was only getting about 5 being dropped, so this was a big improvement from earlier versions, but not quite good enough. Then finally, this is the working version, so this has no IO wait states. We're using the 16 megahertz clock, and we've also got the optimized code. And what you can see over here is when we're reading the first byte here, this did actually require 2 status checks. That when we were doing 2 status checks, it was happening in 21 microseconds, but under normal circumstances, when there's only this is the data byte, status comes back okay, reads next data, we're actually able to read subsequent bytes in 14.5 microseconds. Now this is now actually faster than what the DMA was running at, so hopefully with these improved timings we can now actually keep up. We do still occasionally get the odd error, but floppy disks are generally pretty unreliable. Most operations are set to repeat 3 or 4 times anyway, so generally if there is a problem then it will repeat it and hopefully succeed. So the next problem is that By default, the floppy disk controller is normally stopped by the DMA, TC or end of process signal. So this is basically the DMA controller saying, I've got enough data now, you can stop. By default, the floppy disk controller has the multi-track bit enabled for read and write commands. What this basically says is once you've read one track, do the other track as well, so the two heads. And the end of track in the parameters passed into the read and write is normally set to the maximum number of sectors. So for the high density 1.4 meg floppies, this is 12 hex or 18 decimal. So there's 18 sectors per track. The problem with this is that you end up actually reading up to 36 sectors when you only want one. Now, under normal circumstances, the DMA controller will send the terminal count signal to the floppy disk controller and say, that's enough, go on to the next request. Now, what the PC Junior does, when it's passing the end of track parameter in on reads and writes, it sets it to the last sector it wants to read, not the maximum. And then it handles this sort of end of track error, end of cylinder error, and checks that the number of sectors that it's requested matches those read, and then it succeeds. This shows the section of the PC Junior BIOS from the technical reference guide where it calculates the required end of track parameter for the number of sectors to read. So let's take a look at a few of the code changes that are different from the previous video where I went through most of these changes. So mainly in the two floppy disk routines here. If we have a look at this one first, I'll skip through the things which aren't important. So the specify byte where the no DMA was actually hard coded in the send specify command, it wasn't actually picking up the parameters, so I had to override that value there. Then the read commands and the write commands which are sent to the floppy disk controller, the PC Junior uses 4.6 rather than E6 and 4.5 rather than C5, and this is because some of these other parameters here were zeroed for the PC Junior, so that is now being done. And this is where we're handling the end of track terminal count replacement. So what this does is it works out based on the current sector, the number of sectors requested, it works out what the end of track should be for this particular request, subtracts 1, and then when we send out the command data, it means that the end of track value, rather than being 12 hex, it will be the number that we're actually expecting. Now, if we're having to ask for 12 hex sectors, then in fact it will still be 12. But if we're only asking for one sector, for example, for the boot sector, we might only have a value of 1. And then the changes to floppy 1. So I did come across a bug which I suspect wouldn't be obvious with the BIOS if using interrupts, because the code will probably only get hit once the interrupts are occurred, in which case the floppy disk controller was ready to send the results. But when using programmed I/O, this particular check here, which was masking out some of the status bits, then it was testing specifically with this value here, which basically says, apart from the status bit, FTC status busy bit, set all the others to 1, and this wasn't actually doing what I think it was supposed to do. And so in fact I've changed this, and in fact this seemed to make code work. So it's unlikely to be an issue if you're ever using DMA, but it was a problem for programmed I/O. The checkstat results is a slightly different version of the checkstat2 routine that I talked about in the previous video. The criteria on which the checkstat results was just the execution mode flag, whereas the other routine actually had slightly different conditions. So this is the checkstat results, which basically is looking at the execution mode in the status register, whereas the checkstat2 was using the sense interrupt status command and finding the interrupt status. So these two this procedure didn't exist previously, but I used the basis of this for doing it. Number trans is the code that actually calculates how many sectors have actually been read, and then the RWOPN operation is the bit that actually does the majority of the code. So if you have a look at the read operation, so you can see here that CX was used for an address to jump to this bit of code, so it's we can use it for what we want. And so what I have done is use CX for putting some of the status values in there, so that when we're actually doing the main loop, so I did separate out the first read from the rest of the data, because there seemed to be some issues with the first byte being read, so I needed to optimize that. But the main loop that actually does most of the processing, you can see here that we're reading in the value, we're testing it against this value that we've created above, and we're able to do both the jumps actually on that single test. In particular, jump not sign works specifically on the D7 bit, which happens to be the ready one, so it's quite handy. So it allows us actually to avoid doing an extra test here, and that actually did save enough cycles for us to be able to actually do this fast enough. Then we have to change the register we're using from the status register to the data. We read the data, we use a string store, which again is faster than doing this with individual instructions. We change the port back to the status port, and then we're using BX here to jump. Again, this is saves a few clock cycles, so the value for BX is actually identified up here. So this loop here has been optimized to be as tight as possible, and certainly running at 16 megahertz, this is able to actually keep up. Unfortunately, didn't seem to be able to keep up at the base 14.3 megahertz clock. And I have done similar things to the write loop and the verify loop, although I must admit I haven't been able to test these very thoroughly yet, so I will look at doing that over the future weeks. So it's also having high error rates with the floppy disk access, and I think this was the main reason why some of the later versions of MS-DOS wouldn't load, because they required significantly more disk accesses. So certainly MS-DOS versions after 2.10 would fail, and I think it was because of this issue. So what I have done is reformatted all of the MS-DOS disks I'm using for this on the floppy disk drive that I'm using in the Breadboard PC, and I have got an old Dell computer that I can plug this into, which uses the same drive, and then that seems to have made quite a bit of difference. I'm just basing these on the minimum OS, so this is just what you get with a format /s. So you get io.sys, ms-dos.sys and command.com. It just makes it a bit easier when you're trying to trace through all the reads and things, not having all the directories and file allocation tables cluttered up with all the rest of the stuff. And now I'm pleased to say, in addition to booting PC-DOS 2.10, I have now been able to get this to boot MS-DOS 3.3, 4.01, 5.0 and even 6.2.2. So what we're going to do now is to have a look at this and actually boot up all these different MS-DOS versions. I will speed up some of the loading, certainly the memory testing and some of the loading of MS-DOS can take a little while on this old computer, certainly when we get to some of the later versions of MS-DOS. Okay, so I've got a pile of operating system disks here, and we're just going to power on the Breadboard PC. I do occasionally still get errors, so might need to reboot a few times. I'll speed things up during the memory testing and floppy disk loading. So this is loading PC-DOS 2.10. I do need to put the dates. For some reason the real-time clock seems to have stopped working, so I'll need to have a look at that a little bit later. So we have PC-DOS. So that's working there. So now we're going to try 3.3. So that's DOS 3.3.0, I think, in fact. Okay, so if we do clear screen, and DLL. So there's not very much on there. I will actually load up some more files on here, but it's just sufficient to actually prove that we're able to boot MS-DOS 3.3 now, which was one of the goals that I had in the previous stage of the project. So the fact that now I'm able to do this is very pleasing. So now let's try. This one is the debug version of MS-DOS 4.01. So this was the one that I built from source in some of the earlier videos. So you'll be able to see in the description below all of the various videos they've got here, or the whole playlist for the Breadboard PC. So this one basically will produce lots of debug outputs as we reboot. Okay, so we have MS-DOS 4.01 there. If we just see clear screen, You'll see there's quite a lot of messages come out, and if I do it again, you might just be able to see the top of the screen there, directory of a command.com and all the other debug information there. So that's the 401 working. Let's try 50. Okay, so that's MS-DOS 5. I do also have an MS-DOS 6.2 disk here. I'm not sure if this one is working, but we'll give that one a whirl as well. Okay, so we now have MS-DOS 6.2.2. And just to round this off, what I will just do is try and boot up MS-DOS 7 or Windows 95. Now this won't work because we don't have a 386 processor, but we'll just check to see if that's working. As expected, this version of Windows requires a 386 or better processor. So what it does indicate is that all the versions of MS-DOS I wasn't previously able to load, I am now able to load. I will try and add some more files to those to make the disk a bit more interesting, but it's achieved the purpose of using programmed I/O. This actually seems to have got it working more reliably. I did try all these floppy disks in the BIOS with the DMA enabled, and it still wasn't reliably loading a lot of later versions, so there is still a problem with DMA on the board. But the fact that I've got the PIO, programmed I/O mode working is good. And showing now boot all these versions of DOS. Kind of gone back and completed the boot and run DOS from floppy disk. I was originally looking to be doing 3.3 MS-DOS as well as the 2.1. So now they'll be able to do 3.3, 401, 5, 6.2.2, and even attempting to run Windows 95 as well. So in the next video, what I'm going to start looking at doing is the IDE disk controller and IDE BIOS. This is going to allow us to install DOS on the hard drive, and this should really make the necessity to use the floppy disk really, apart from perhaps using fdisk and formatting the hard disk drive, then really we probably won't need the floppy disk drive much after this. So if you don't want to miss out on future videos, if you can hit subscribe, and if you can also hit like as well, that'd be useful, just because it makes the videos available to more people. Thanks for watching.